Now, cosmology has to do with the universe. We have a wonderful universe that we live in, created by God. You've all seen this planet before, I presume. There's some other planets here. Last night we did have the telescope up for a while, so you could see Jupiter with the 4 stars. And there's some beautiful nebula out there. And as we move further away, we get galaxies. This is a beautiful one, the Sombrero galaxy. And if we move further out, we get clusters of galaxies. And if we move further out yet, we get this beautiful picture. Every dot that you see on there is a galaxy. This is taken with the Hubble telescope. And it really is marvelous, all the variety and beauty that we see out there. Now, what is cosmology? Well, cosmology is the science of the universe as a whole. So the object is to describe and to explain the universe, okay, but particularly the astronomical aspect of it. In recent years, the last few decades, especially with the Hubble telescope, there's a tremendous amount of new observations that are there. Some of the observations might answer previous questions, but in general, every time you have a question that's answered, you have many more questions that are raised by the observation, because creation does seem to be much more complex than we might expect it to be. And what we try to do then is in cosmology is to explain the data in terms of cosmological models. Now, a model is basically a set of mathematical equations, if you like, with which we try to represent reality, or at least a simplification of it. So cosmology, we forget about people, we forget about life, and basically we're dealing primarily with matter and energy and how these then form in stars, galaxies, and planets. Let's look at some history of cosmology. First of all, you may have seen this diagram before. In a number of modern textbooks on Genesis, this is said to be what the Bible teaches us about the world. So it's said that the earth is flat, that it's floating on some ocean, that there is a firmament, okay, which is a very thin, hard sheet. Fixed to the firmament is the sun, the moon, and the stars. Beyond that, you get the waters above the firmament. Beyond that, you get the heaven of heavens. And this is said to reflect ancient cosmology. There's a few problems with this diagram. The first problem is that you don't find this diagram anywhere actually in the ancient literature itself. So this is largely an artistic reconstruction, if you like. And if you look at this closely, you'll find there are some strange things, because if the firmament is fixed, so if it's just a hemisphere situated on the pillars of heaven, right there, and if the sun is fixed to it, and the moon, then how can it ever be dark at night? And secondly, what happens at night? If you allow for a movement, then you find, well, as soon as the sun hits these mountains here, what's going to happen to it? Is it going to go underneath the earth, or how does it ever come up at the other end again? And so I don't really believe that this is what ancient man believed the universe was like. And the difficulty is that if you go back to earlier than about 500 BC, you won't find any science, you won't find any cosmology. What you do have is mythology, stories about how the universe was created by the various gods, okay, Greek mythology, Egyptian, Babylonian, and so on. And the argument by many scholars, biblical scholars, is that the Bible must reflect ancient cosmology, which they figure looks like this, because the Bible writers weren't inspired to know any more about such things than the surrounding nations. And that therefore, even though Genesis doesn't mention these pillars, or doesn't say that the firmament was solid, that must have been implied, because it's presumed then that biblical cosmology will be the same as ancient cosmology. But all Genesis 1 really says is that on the fourth day, God created the sun and the moon and placed them in the firmament. It doesn't say anything at all about the firmament being a thin sheet, or that the sun and moon and stars are fixed in that firmament. In fact, Genesis 1 tells us that the sun, moon, and stars were created to provide times and seasons and so on. And if you're going to have times and seasons, that means that the moon has to move with respect to the sun. So that means that these two can't be fixed with respect to each other. So that means that when the Bible talks about the firmament, it can't be a solid disk, but there must be movement within it, because otherwise you can't have the moon moving through its various phases once per month. And also, if you look at the writings of ancient men, you'll find that they numbered, or they named the constellations a couple of thousand years BC already. The constellations form a sphere, if you like. So the ancients never visioned the sky as just a hemisphere, but they would have envisioned it as a full sphere, and probably with a spherical Earth inside it. There's a well-known myth that people believed that the Earth was flat until Columbus came and discovered America. There's no truth in that whatsoever, because people knew that the Earth was round at least at 500 BC when they started writing about it, and I suspect much earlier than that as well. So the earliest real cosmology that we have occurs with the Greeks around 500 BC. They started to try to explain the universe in terms of scientific concepts rather than mythology. So here we have the universe according to Plato. So note that at the Earth we have the center, then you've got water, then you've got air, then you've got fire. Those are the four elements that you find of Greek philosophy or Greek science. Beyond that, you get the ether, if you like. Then you get the moon and the various planets. And beyond that, you get a firmament, then a shell of stars way out there. And it was thought, if you want a physical model, that these were like glass shells, and that these shells then would rotate amongst each other so that you have a fixed outer shell, but then you have shells moving then at various speeds. So this is Plato's cosmology before 400 BC. It's a simplified representation then of reality. Note the 5 elements that I've discussed there. And a key feature here is that we have circular motions in the heavens. So Plato thought that in the heavens everything is perfect. So circular motion represents perfection, because you always come back to the starting point and repeat. Whereas on the Earth, things are corrupt, and there the motion is up and down rather than circular. Now, in the Middle Ages, the cosmology then was very similar. Again, you have the Earth at the center here, the different spheres. But notice that once you get to the stars beyond that, you have heaven. So this is the habitation of God, if you like, and the elect in Latin. And so here we have then a representation of earth and heaven. So models, cosmological models, will incorporate, they may incorporate theological and philosophical beliefs. Okay, note here then that we have heaven beyond the stars. Here's another picture of medieval cosmology. This one goes one step further. In fact, you have heaven beyond there, but note that here we have purgatory. And inside the earth, on the other side, we have hell with 9 different levels. You might be interested to know that the 3rd level of hell is reserved for gluttons. And on the other side, we have Jerusalem and the dark wood. So with these models, then, we have a picture of reality, okay, tied in very closely to worldview, okay, with basic philosophical and theological beliefs. Now, the trouble with these models was that all the motion is circular, and if you look at the actual motion of stars, then you'll find that as Mars comes along in the sky, it's going the wrong way there. It goes along in a circle, but then it does a little loop like that, and then it continues. So explaining that loop was a problem for medieval cosmology, and one way to get around it was to say, well, motion is a bit more complicated than just a circle. So instead of planets moving in a circle about the Earth, we make the Earth a little bit off-center, and then we add a circle on a circle. It's called an epicycle. And as this epicycle, as this point circles around F itself circles around the Earth, and the motion you have there goes like this, and you have this little loop. So he found that, this was Ptolemy, okay, a Greek astronomer, about 100 AD. He found that this could represent the motions quite well. And he was still a little bit out, so he ended up having another circle, an epicycle on an epicycle. And you can see that if you add enough epicycles here, you can get any accuracy you want. We have something very similar to this in modern physics. It's called a Fourier series, that you can fit a Fourier series to any set of data, okay, by doing just what Ptolemy did. Now, there is a problem with this, because if the planets are doing these complicated circles, how can that be if they're fixed in these glass disks that are rotating inside each other? Okay, that doesn't really work, because then you have to move through the glass. So this will only work if you have something that's non-solid, something that's fluid, or nothing at all that will do that. So the question that was raised to Ptolemy was, well, how does this fit in with Plato's cosmology, where you have these glass spheres? And Ptolemy argued, he said, well, my model doesn't really represent reality as it is. It's just a useful fiction that you can use to predict where the planets are going to be in the past and also in the future. So he argued that his model was just a theoretical construction that was aimed at saving the observations, so reproducing the observations and being used for prediction, but that it really had nothing to do with any kind of a deeper physical reality. So this raises the question, what is the use of a cosmological model? And so there's two responses to it. The response by Plato and Dante was that a cosmological model, is a simplified qualitative representation of reality reflecting philosophical and theological truths. Whereas Ptolemy would argue that a cosmological model is a simplified set of mathematical equations yielding quantitative accuracy, useful for calculation and prediction. Now, so this whole question of how cosmological models should be viewed came to the fore much more prominently in 1543 when Copernicus published his model. And Copernicus said, actually, Plato is wrong. The Earth is not at the center of the universe. Actually, it's the sun that's at the center of the universe, and all the planets are rotating around the sun. The Earth is just another planet, and the stars are in a fixed shell around the sun. But in his introduction, which was probably written by someone else, it says that this model is just presented as a useful fiction which helps us to simplify making predictions of where the planets are going to be. So the question that was raised was, should we view this model of Copernicus as just a useful fiction, Or does it really represent reality as it is beyond the observations? There's a lot of discussion about this in the late 1500s. Most astronomers used the model as a useful fiction, but didn't really believe that it was true. One astronomer in particular, Tycho Brahe, he argued that we can get exactly the same observational effects if we take the sun as the center of the solar system. So here's the planets going around the sun. Here's a comet also going around the sun. But we can still keep the Earth at the center as long as we have the Earth going around, or the sun going around the Earth and carrying all the planets with it. So now the question that arose was, which of these models is true? They both give you exactly the same observational results. The one has the Earth fixed at the center with the sun moving around it. The other one has the sun fixed at the center with the Earth and everything else moving around it. So what do you think? Which one of these models should we take as true? When I ask my students, they all say, well, obviously the one by Copernicus and not this one here. But then if I ask them, well, why would you say that? How would you prove it? Then usually the response I get is, well, that's what the textbooks say. To which I respond, do you believe everything you read? Because what we have to deal with here is the question of absolute motion. Now, in science, you can observe relative motion, but to go from there to absolute motion, you have to make a choice as to what reference point you're going to take as being absolute. And that is something that has to go beyond the observation, so that means that it's going to be a philosophical choice as to which one you prefer. So Copernicus wasn't widely accepted until a little bit later. Now, one of the difficulties is that a cosmological model you can use to bridge the gap between your conception of reality, your worldview if you like, and appearances. So a model then is one that you can ground in your biased point of view and make the connection there between the observations as showing that the observations are consistent with your worldview. But the thing is that there's different ways you can do that, and you can tie in different worldviews with different models. So it turned out that Copernicus was not widely accepted until about 100 years later, until his model was tied to a physical model after about 1650. Descartes came up with a model of the universe, a physical model in which the Earth was moving. And according to Newtonian mechanics, you can measure absolute motion, certainly as far as rotation is concerned, by looking at effects such as centrifugal forces and so on. And if you accept that definition of absolute motion, then the Copernicus model will be favored over the Newtonian model. The trouble with that explanation is that Newton is out of date, because after Newton we have Einstein coming with relativity, and if you take general relativity, you get exactly the same results if you take the Earth as fixed and the universe rotating around it, or if you take the universe as fixed and the Earth moving in the universe. So the two are identical, and that again raises the question, what should we take as absolute motion? The interesting story here is that in 1993, the Pope admitted that they were wrong in condemning Galileo back in the 1600s for arguing that the Earth was moving. And shortly after that, there was an editorial in the British scientific magazine Nature, where the editor said it's high time that the Church recanted of its position. However, Galileo was probably too good a scientist to consider motion in any more than a relative sense. So what that means is that the editor of Nature was really saying that the Church was right in the first place to reprimand Galileo for claiming that he had proven absolute motion. So the thing is that it's not really a scientific question because it has to go beyond the observations. So for example, if we look at this from a biblical point of view, if for example we consider that heaven exists, that it exists somewhere in space, maybe a multidimensional space, and that it defines absolute motion, then there's nothing wrong with considering that Earth might be fixed with respect to such a reference frame. Of course, that doesn't give you any observational consequences, which means that it doesn't really have any scientific implications as such. But let's move on. So there's a question here, how do we choose? So it depends again how we define your absolutes. Let's go on to more recent things, the Big Bang. Here's a conceptual diagram of it. So as the theory goes, originally there was nothing. Then we get a quantum fluctuation, zero energy. The universe jumps into being. It expands very quickly. After about 400,000 years, the light separates from the matter. Okay, what that means is that you can't observe anything that happens in the first 400 years. There's no light coming from that region at all, which means that that part is beyond observational proof or disproof. And after that, we get stars being formed. First stars, 400 million years, then galaxies, then we get the expansion, and so on. What is the observational support for the Big Bang? Well, galactic redshifts. Okay, I mentioned that this morning, that if you look at galaxies, you'll see they're shifted towards the red. I'll explain that a bit more in a few minutes. If you look at the abundances of elements in the universe, the Big Bang predicts about 75% hydrogen, 24% helium, the rest higher elements. Okay, that's roughly as observed. And the microwave background radiation, if you look in any direction with the radio telescope, you'll see radiation of about 3 degrees Kelvin. There are, however, some difficulties with cosmology in general. One problem is that there's only one universe. So you can look at many different dinosaurs and collect them and look at common features, but there's only one universe. So we don't know if our universe is special or whether it's just a normal average universe. There's only one to look at. Second difficulty is that you can only observe from one position, from the Earth. We might assume that the universe is the same everywhere else, but you can't really prove it. It is an assumption. The third difficulty is that you can observe only light coming from stars or radiation that you can pick up with radio telescopes. There might be a lot of other things out there that you can't see, and hence that you can't put into your model. For distant objects, they're very hard to distinguish from the background. Distances are hard to measure. And the conditions in the early universe, okay, so the first part of the diagram is very hot then, very dense, and we have conditions here that we can't reproduce in the lab. So that means that we're dealing with parts of physics that we can't really test directly. Moreover, in Big Bang cosmology in particular, we assume that the laws of physics that hold here and now hold everywhere, that general relativity is true, that high energy particle physics holds. We assume materialism, that everything can be derived from matter, that nothing else exists, that mind can come from matter, and so on, that there's no non-material causes. And the difficulty is, how can you verify this? There's two types of problems in cosmology with verifying things. Untestability of the first kind means that in principle you can't test it. For example, you can't observe anything before 300,000 years after the Big Bang. So there's no light coming from that part, so we can't really test the observations. In some theories of physics, you've got 11 dimensions or more. You can only observe the 3 dimensions that we actually see. So we can't observe the extra dimensions that are postulated. We can't reproduce the high energy to confirm hypothetical particles in physics. There's also another kind of untestability, things that are effectively untestable. If you look at the standard model of particle physics, it has 20 different constants, fudge factors. You can change these constants as you like to fit the observations, which means that if something doesn't fit, you can adjust something else again, so that you can't really test the theory because you can just keep on adjusting things. The Big Bang itself has various problems. If you look at galaxies that are very far away, they seem to be of the same nature as galaxies that are close by. So you'd expect them to look younger, that there would be a difference, but there really isn't. We've got huge structures of galaxies that seem to be there already right in the beginning. So how do these structures form so quickly? If you look in different directions, you'll find different directions of the sky have the same temperature, which means they must have been in contact. They must have mixed at some point. This is called the horizon problem, but there doesn't seem to have been enough time for that to happen. The first stars are hypothetically produced from hydrogen. Once the stars get older, the temperatures get high, and you produce heavy metals. So the first stars, you won't expect to have any heavy metals. Later stars will, but it seems that some of the earliest stars have heavy metals already. So the question is, how did that arise? Another problem, some cosmologists say that energy is not conserved. So Harrison, in a standard textbook on cosmology, says the conclusion, whether we like it or not, is obvious. Energy in the universe is not conserved. The conservation of energy principle serves us well in all sciences except cosmology. But conservation of energy is one of the most basic laws of physics. So if you have to do away with that, then you've got a serious problem. There's also a difficulty with the cosmological constant. It should be much larger than is observed. And also, a lot of the redshifts don't fit into the pattern. Some nearby stars have high redshifts, which you wouldn't expect. Many other redshifts come with at certain particular numbers, so they're not continuously redshifted, but they seem to have jumps, which is hard to explain. And also, more recently, most of the mass of the universe is postulated to be missing mass, which means you can't see it. And also the universe seems to be expanding, which means that there's also a mysterious type of dark energy. These are all things that really aren't observed in the lab. So the question is, how do we explain that? Now this is the difficulty, that you can always, as we saw this morning, save a favored theory by fixing it up. So for example, to save the Big Bang cosmology from falsification, the horizon problem, that the temperature seems to be the same in all directions, inflation was invented. So inflation is a theory that right after the Big Bang, in the first thousandths of a second or so, the universe expanded very rapidly, much faster than the speed of light. And that allowed it then to solve this particular problem. The trouble with inflation is that it predicts that the mass of the universe has to be a particular amount, and the actual mass of the universe that we see is just a few percent of that. So inflation seems to disprove Big Bang cosmology, but you can save inflation by postulating that most of the mass that's there, it is there, it's just that we can't see it. So this is dark matter. The difficulty with the dark matter theory is that if you look at theories as to how matter comes from energy, then you can only get so much of the matter that we actually see. So the matter that we can't see has to be quite different from the matter that we do see. Then to save the dark matter, we have to have new forms of matter which aren't observed as yet, and so on. So no matter what observations come up, you can always save the theory, Big Bang cosmology, by making adjustments in it. So I gave this quote already this morning by Quine. You also saw it in the lecture after that any statement can be held come what may if we make drastic enough adjustments elsewhere in the system. So we can construct a model with any given feature if we make drastic enough changes elsewhere in the model. So let's look at the redshift in a bit more detail. So lines in the spectra from galaxies are shifted to the red. So here you have a typical spectra of light. So light from the galaxy, if you look at the different wavelengths, you see different lines here corresponding to different elements. So different elements will have a different pattern of lines. So these might be the pattern due to hydrogen. So you can recognize what element you have in the galaxy by looking at these lines. And if you look at spectra from galaxies, you'll find that this particular line here is going to be shifted towards the red depending on how far the galaxy is away from the Earth. So the further it's away from the Earth, the further it's shifted away from the reds. And all of these lines will be shifted by the same proportion. So you'll find that the whole spectrum is moved over. So you can measure how much it's moved over, and you can compare that then with your distances. And from that you get what's called the Hubble relation, which tells you how fast the universe is expanding. Now, do redshifts support the Big Bang? Well, redshifts would be expected if galaxies are moving away from us, because if something is moving towards you, then you'll find that the wavelengths are bunched more closer together, it'll be shifted towards the blue. If it's moving away, then the wavelength will be longer and it's shifted towards the red. It's just like when a police car comes up behind you, you hear the siren going, and you find that as soon as it moves past you, which is always a good thing, then the pitch will change as well. You'll find a change in the pitch as it goes past you because it's moving. The vibrations that are moving from coming more closer together to being spread out. So redshifts are interpreted as being caused by the expansion of space. As space expands, then it sort of stretches the wavelengths so that we get this shift towards the red. Now, we looked at this already this morning. You can explain the galactic redshifts by having expansion of space, but you can also explain it by having motion through space, gravity, decreasing speed of light, shrinking atoms, increasing mass, and tired light. The interesting thing with the tired light theory, I mentioned that this morning, as light moves through space, it gets tired, it loses energy. This theory was discussed in the 1920s, and it was calculated that the light lost by, or the energy lost by the light would go into heating up the interstellar matter, and the temperature that they had expected to find was 3 degrees, which is exactly the temperature that you get in the microwave background radiation, which is used as a proof for the Big Bang. But it was predicted already then in the 1930s as a consequence of the tired light theory. Now that means, because you have all these different interpretations of the redshift, that you could have alternative cosmologies. Here's one by M.C. Escher. But you have a lot of different theories. Some theories say that there never was a beginning, that our universe started from an expansion in a previous universe, and that one started from an expansion of a spot in the universe before that, and so on forever. Alphen thinks that the universe didn't start from a point, but started off from a previous universe which contracted, but then it reached a minimum size, and now it's expanding again. So his universe existed forever. It's just that there was a previous expansion. A number of cosmologists have looked at universes that are static. They're not moving at all, and the redshift is caused by something else, either tired light or a big gravitational source at the other end of the universe. But you could also have a biblical cosmology. So I want to have a look at that. There is a number of goals, 2 different goals of biblical cosmology. One would be to critique non-biblical cosmologies. So for example, you could look at the Big Bang and consider the problems that they're having and the difficulties, and considering that to be a disproof. So you could look also at evidence of recent creation. But another way of doing it is to set up your own cosmological model, a bit more constructive, and trying to explain reality within a biblical framework. Now, there's different things we could look at. Usually the question of origins is prominent. I'm not sure that should be the case, but that is the case. And the main challenge there is how to explain starlight in a big universe. So if the universe is 14 billion years in radius, if you have galaxies that are billions of light years away, how can the universe only be 6,000 years old? Yeah, there's a number of explanations that you could come up with that, a number of possible strategies. One is taking an instrumentalist view of science, where theories are just useful fictions. Then you would argue, so this would be the position of Gordon Clark, okay, Christian philosopher. He would argue that theories are just useful fictions. They just allow you to get from one set of observations to the next. So anything beyond what you see shouldn't concern us. So this whole question, he would argue, is not really an empirical question. It's just a question of theoretical explanation with which we need not concern ourselves. A second approach would be to argue that we've got different clock rates. So this is the position of Russell Humphreys, John Hartnett. They would argue that there's different clock rates on the Earth than far away, so that the universe far away might be billions of years old. It's just that the clock on the Earth went a bit slower. Or if you like, the clock out there went faster, so that while you have 6 days here on Earth, billions of years have gone far away. Or you could argue that the speed of light has changed, that the speed of light was infinite in the past. This is the theory of Barry Setterfield, and that the speed of light was infinite shortly after creation, that it meanwhile has slowed down to reach its present speed now. You could also argue that you have an illusionary history. I'll talk about this in a minute. This is a theory by Tipler. He's not a Christian at all. Or you could argue that we have mature creation, that the universe was created with starlight and everything all together. Let's look at some of these in a bit more detail. So if we look at the different clock rates, there's a book by Russell Humphreys, 1994, called Starlight and Time, where Humphreys argues that the universe is like a white hole. So in a black hole, everything condenses into nothing, if you like, but a white hole is the opposite of that. So all the light comes out of it for nothing. So you get this expansion centered on the Earth, and he argues from that you get different clock rates. I don't think it works because if you look at that model from general relativity, which is what he uses, then it seems to me that either you get no actual time dilation at all, or if you do get time dilation, you get blue shifts rather than red shifts. Now, Humphreys has meanwhile taken his model and tried to get around that. I'm not sure that he has quite succeeded with it. A second model is by John Hartnett. He's written a book called Starlight, Time, and the New Physics. This is a sophisticated cosmology based on 5 dimensions. So he has 3 dimensions of space, time, and then also speed. So speed is a factor here as well. And again, he has the universe starting off with a big expansion centered on the Earth. And then he claims that he can get the different clock rates coming out of this, so that he has 6 days happening on the Earth, while billions of years occur far out in the universe. Now, the problem with Hartnett's model is that he spends the whole book discussing his model, but there's only a couple of pages where he actually deals with the 6 days and explaining that, and I find that part of it, it has a bit too much hand-waving. He needs some more detailed calculations, and he has to look at some of the implications that come from it. Because if you have an expansion close to the Earth, you'd think that you still have some consequences of that that are left. So the difficulty with these models is that they are what I call ad hoc, that they're sort of invented to explain the observations, but they don't really predict any new observations. And they still have to be worked out in detail. Another difficulty is that for the nearby objects, such as the sun and the closest stars, maybe even our galaxy, they still need mature creation. And if billions of years have happened far out in the universe, that means that a lot of the astronomical evidence for a young universe is sort of thrown out of the window, because they're saying, well, actually, billions of years could have passed during that time, so that those arguments are of no use to us. And I would say that if you want different clock rates on the Earth rather than far away, an easy way of doing it is to say, well, why don't we just accept the biblical unit of time as a day, but postulate that the rate of rotation of the Earth was a lot slower for the first 3 or 4 days. So then you could have had a couple of days, each being 1 billion years long, but each is just one period of light and darkness. That would give you almost the same effect as they get with their models, but a lot simpler. The only difficulty with that that I see is that you have vegetation occurring already in day 3. So that means that half of the universe, or half of the Earth, would be in darkness for a long night, and the other half wouldn't see any night. So that would be one thing that you would still have to explain. The other possibility is to go for variable speed of light. So there's various possibilities here. You could postulate that c varies with time. So Barry Setterfield, for example, says that c is the speed of light, that it was infinite at creation, and then it died down. One good feature of his model is that it can also explain the radioactive decay, because the rate of radioactive decay is tied into the speed of light. So you could also have that being much faster in the time as well. So you could kill 2 birds with 1 stone, as it were. The trouble with this theory is that precisely now, the year 2010, when we can measure the speed of light quite accurately, it seems that the speed of light isn't slowing down anymore. It's fixed. And if you look at the observations for the last 300 years, there might be some evidence that it's slowing down, but the error bars are quite large, so there's a lot of discussion and dispute as to whether the speed of light has really slowed down or not. The other problem is that if the speed of light was much greater in the past, then light that we see now from distant galaxies should have been much greater when it left that galaxy, which should be reflected then in the conditions then. For example, a Doppler shift, the speed of the galaxy, the speed of rotation of the galaxy, things like that should be still reflected in the information that we see, and we don't really see that. So you could argue, well, maybe the speed of light didn't change with time, but it changed with position. So there is a theory that says the speed of light is very large far from the Earth, maybe infinite at the edges of the universe, and as it gets closer to the Earth, it gets smaller until it reaches the Earth. Okay, I think that has the same problem as Setterfield's theories, that you would expect to see some observational features of that in galaxies far away. You could get around that by saying, well, maybe the speed of light is very large between galaxies, so that it's the same close to the galaxies, but once you move between galaxies or between stars, it moves a lot faster. So you could postulate that the speed of light somehow is fixed to the value of the gravitational field, and that would explain how light can get here so fast. So another theory is that light varies with direction. There's a very recent paper in the Creation Answers journal, I think it is, by Jason Lyle. He's got a book here where he argues that when you measure the speed of light, you also always have to measure it in 2 directions. You can't just measure it going in 1 direction. So he argues that the speed of light is infinite when it comes from a star to us, and it's twice as slow going back, so that on the average it's c, but that the light from a distant star reaches us instantaneously pretty well. Now I think that that has problems as well, because the speed of light also has to do with what's called the permeativity of space, certain properties that you have, and I don't think you can have it infinite one way and just see going the other way. But this is another theory that you'll find in the creationist literature. So it's in the September Journal, just came out last week, I think. Now, there's another theory by a non-creationist, Tipler. He's a cosmologist. And he's written, it's thought to be impossible to construct a falsifiable theory consistent with the thousands of observations indicating an age of billions of years, but which holds the universe is only a few thousand years old. I consider such a view to be a slur on the ingenuity of theoretical physicists. We can't construct a falsifiable theory with any characteristics you care to name. So he's not a creationist, but he's saying, well, look, if the creationists want to create a cosmological model, there's no reason why they can't do it. And here's a possible model. Now, this is the name of the paper. Came out about 20 years ago. And in this paper, he claims, or in this paper, he postulates that if the Earth is surrounded by black holes 1,000 light years away, then these black holes will cause illusionary histories. This is due to some kind of a quantum effect. I'm not going to go into detail. So he says there's all kinds of different histories that might be consistent with a universe that's 6,000 years old. And he says, if you think that's strange, it's no stranger than quantum mechanics, because the main view of quantum mechanics is also that there's all kinds of different histories that exist at the same time, and that all histories are, to some extent, illusionary. Now, most of the theories that I've looked at, such as Humphreys and Hartnett and others, have mature creation of some sort. They all have mature creation for the sun. Now, if the sun was created as a unit, would that include light or not? Well, I would argue that it would include light, because if you look at the sun as an object, it consists not just of mass and gas, but you've also got photons. You've got light there. You've got light pressure. So if God's going to create the sun in one instant, it's going to include all the light that comes with it. But normally it takes light 100,000 years to arrive from the center of the sun, okay, where it's made through nuclear reactions to the surface. So that means that if God would create the sun instantaneously, it would appear to have a 1,000-year history behind it by looking at the light. And you could move on and say, what about a galaxy? If God would make a galaxy, would he just make the stars and not the light? Or would it be with the light as well? Well, if God would make a galaxy in one mature form, surely it would be created in such a way that the different parts would be connected gravitationally, so it would hold together as a unit, so it would function. But if gravitons exist, then you think, well, the light particles must exist as well, so that if God is going to create a universe or a galaxy instantaneously, it would automatically come along with the light, so that if you didn't know that God created it instantaneously, it would have this apparent history. And so you could move on to look at clusters of galaxies, use the same arguments, and then argue, well, why not for the whole universe? If God would create the whole new universe in mature form, then surely this would have the light with it. And if you look at the literature, here I have a quote from a secular cosmologist, George Ellis. He says that if you have a universe created instantaneously, there's nothing unscientific with it. You couldn't disprove it observationally. You could disagree with the premises behind it, but scientifically, you've got a solid case. The theory is free from self-contradiction. It's consistent with all the facts. It doesn't multiply hypotheses beyond necessity. It's beyond future refutation. If you were to ask of our concept nothing more than that they should correlate with our experience, we must accept this model in preference to any other. Nevertheless, it is doubtful if a single person does so. Herbert Dingle. So there's various cosmologists that will agree that you could do it this way. Now, the common argument against it is that God can't create a mature universe, because if he did so, it would be deceptive. So Don Stoner has written, either God's creation testifies it's much older than 10,000 years, or God has deceived us in his creation. And this person writes, if people living today would have been created by fiat creation rather than evolutionary, there would have been no branching pattern, etc. But he argues that since God does not deceive us, I conclude that he created us through evolution. So again, it's the same argument that God doesn't deceive us. And if you go back through history, Descartes, philosopher, he writes, God is perfect, hence God cannot conceive, so God will not permit me to be deceived concerning the truth of those propositions that seem entirely clear to me. So he's arguing my philosophy must be true because it's obvious to me God wouldn't deceive me. Now, one thing that's interesting is that none of these authors consider the converse. And the converse is if God doesn't deceive, should we not take him at his word? So would God deceive us? Scripture certainly says that God cannot lie. But these remarks concern in a covenantal context, meaning that he cannot lie to believers because he has promised to be faithful to us. Now, Scripture specifically says that God does deceive those who are not believers. Particularly at the end times, God sends a strong delusion that they may believe what is false, in order that they may all be condemned who did not believe the truth. And ultimately, all deception is traceable to Satan, the serpent, the dragon of old. Now, I've looked at origins. I'm almost running out of time here. Let me look quickly at a much more important question. How will the world end? Through a big crunch, where the universe comes together again and disappears, or a whimper, where it continues to expand, there's no energy left, all life dies. Does it end that way, or with the return of Jesus Christ? Now, Tipler writes that traditional religion has to come to grips with this, because if this future of Big Bang cosmology is right, then we're just at a low stage of evolution. We're going to have much more highly intelligent creatures, so we're insignificant. Not only that, but we're all doomed to die anyways. So he argues that we have to come to terms with the fact that the universe will last at least another billion years. Now, Hans Kung, the Catholic theologian, writes, biblical miracles are metaphors, not historical events that break laws of nature. And he works this through consistently because he says it's necessary to warn against theological fallacies about the end of the world as much as about the beginning of the world. So he argues we can't take Genesis at face value, but neither can we take Revelation. So basically he's arguing that there's no life after death, that there's no second coming, that we can't take that at face value. But any genuine Christian must believe in the physical return of Christ, so this means that we have to part with Big Bang cosmology at some point if you're a Christian. Now, I was just at a conference in England in July where John Polkinghorne had his 80th birthday, and Polkinghorne agrees with this. He says the basic problem between Big Bang cosmology and Christianity is not the past. He accepts it in the past, but in the future. And he says here we have to break with it. We have to remember that God controls everything. God can change the physical constants, so God can change the universe so that we have the return of Christ and the new earth and the new heaven. But my question is that if God can change the constants in the future to do that, why couldn't he have done the same thing in the past? If we can't accept the Big Bang cosmology as far as its predictions of the future goes, why should we believe what it says about the past? Moreover, reality is more than what we observe. The universe is more than matter. What about spiritual reality? Where do we place heaven? God, angels, demons. These are spiritual beings, but they can have physical effects. And heaven is a physical place, right? Jesus Christ has a physical body. So it must exist somewhere in physical reality, but we can't see it. It's in heaven. It's nearby. Sometimes you can see it if the heaven is opened, such as Stephen and others. But it's there, which suggests that the universe is a multidimensional place, and that the physical reality that we see is just a thin shadow of a much richer reality. Rather than the other way around, the way the secularists look at it is that the physical reality is the real reality and that spiritual reality is just an illusion. So I'm going to skip over this because I'm out of time. How do you explain things? Assessing creationist models. There are advantages to creationist models. They are based in biblical truth. They show consistency between the Bible and the observations. But you have to remember there's always limits here. Many biblical models are possible. Which one is true? Okay, I've given you half a dozen different biblical cosmology. I'm not going to pick any one as being true. I'm saying there's various possibilities out there. There's various ways that you can find theories that will make the observation consistent with the biblical explanations. Mature creation is one possibility, but note that mature creation doesn't explain observational results. It just says, well, this is one way that God could have done it, but doesn't explain why the universe is the way it is. But just because it can't explain that doesn't mean it's not true. These have limited apologetic values because the assessments and choice depend upon your worldview. So what I'm saying here is don't tie the Bible to any particular scientific theory, because if the theory is disproved, then your belief in the Bible might go down the tube as well. The Bible is true whether or not our theories are in accord with it. So we must consider comprehensive explanatory power, and again, remember that worldviews come as package deals. We're trying to explain all of reality, not just physical reality, but also the human condition and many other aspects. So how do we choose a cosmology? Again, I would urge that worldview beliefs are unavoidable. The basic question is, what's the ultimate reality? Is it matter? Okay, Big Bang cosmology. That's how matter evolves into mind. Or is the basic reality mind or spirit, which then creates the material universe? And how do we know truth? Is it through our senses, again, empiricism, through our reason, rationalism, or through God's Word, the Bible? So in conclusion, let me say there is a huge gap between cosmological data and theory, that cosmology needs presuppositions, many of which are unverifiable because we can only observe a small part of the universe. The same data can be explained by many cosmologies. Any favored cosmology can always be saved by ad hoc devices. Cosmologies are assessed in terms of one's worldview, and materialist and biblical cosmology differ not just on origins, but also on the future and the nature of reality. So biblical cosmology gives meaning to reality, purpose to life, hope for our future. I'm out of time. Thank you.